everyone, welcome back to our last module. We will be discussing about greedy algorithms for the minimum spanning tree. Let's start with the definition of a minimum spanning tree, but before we discuss about the minimum spanning tree, yung spanning tree muna. So, a spanning tree of a connected graph G is a connected acyclic subgraph of G. So, since it's a tree, of course, dapat acyclic yung subgraph ni G that includes all of G's vertices. So, parang you can imagine the spanning tree of G as a tree representation of G. So, andun lahat ng vertices ni G, but nagtanggal tayo ng some edges of G para maging legitimate tree si spanning tree. Okay? So, of course, there's a lot of possible spanning tree of G. And may isang spanning tree that is called the minimum spanning tree. It's called the minimum spanning tree because that spanning tree has the minimum total weight. So the total weight here is the summation of all the edges that is part of the spanning tree. So suppose this is our input graph. Marami tayong possible na spanning tree out of this graph. So the first criteria is, of course, dapat lahat ng vertices ay included doon sa spanning tree and the total number of connected component should be 1. And this is another example of a spanning tree of this graph. So, the weight of this spanning tree is 6 plus 4 plus 1, which is 11. And the weight of this spanning tree is 2 plus 3, 5, 6, so 6. So, the minimum spanning tree is the spanning tree with the minimum total weight. Take note that it's just a tree that has no orientation. So, walang root node, walang order yung mga subtrees. So, it's just a subgraph na acyclic. So, yun yung spanning tree natin of a graph G. So, the minimum spanning tree problem is, given a graph that has edge weights, the output is the minimum spanning tree. So, the representation here is a tree, T, with set of vertices V that is equivalent to yung V ng input vertex, and we have E prime, and E prime here is a subset of edges ng original graph, and then you have, of course, ginawa ko na lang W prime because this is a subset. Since you have a subset, this is the corresponding weight of this set of edges. So, well, nabanggit ko before that the most intuitive way how to solve a problem is by the exhaustive search. We can generate all possible spanning tree given a graph. Pero, that is exponential in running time. In fact, we can have n raised to n minus 2 na possible spanning tree given a graph G. So, especially if it's a dense graph or a complete graph, mas marami pa yung possible spanning tree. And exhausting all the possible spanning tree and getting the minimum is way complicated than the greedy algorithm for this, which is mas madaling isolve. So, for this problem, we have two solutions. And these two solutions are greedy algorithms for the problem. Number one is the Prim's algorithm, and the second one is the Kruskal's algorithm. For the Prim's algorithm, we are trying to construct the solution. We are trying to construct the tree by growing the tree one vertex at a time. And for the Kruskal's algorithm, we grow the tree one edge at a time. So, yun yung main difference ng Prim's and Kruskal's algorithm. Both are greedy algorithms because we construct the solution or the final tree piece by piece, vertex per vertex, edge per edge. Pero, magkaiba of course ng running time and magkaiba din ng implementation. So, let's start with the first algorithm. So, the Prim's algorithm, as I mentioned a while ago, tries to construct the tree by adding one vertex at a time. So, initially, start with a tree, T sub 1, consisting of one vertex. So, we can arbitrarily we can arbitrarily choose any vertex of the graph G, and we grow the tree one vertex at a time to produce the minimum spanning tree through a series of expanding subtrees. So T sub 1 is a subgraph of T sub 2, T sub 2 is a subgraph of T sub 3, and so on. So nagdadagdag lang tayo ng nagdadagdag ng additional vertex. So for T sub 1, we have one vertex, any arbitrary vertex, and then we add a second vertex. Then that's the T2, so may 2 vertices, hanggang sa makaabot tayo sa tree with n vertices. But the manner of adding one vertex to T sub I minus 1 is by choosing yung closest vertex dun sa T sub I minus 1. So for each iteration, we construct yung next tree by using T sub I and adding vertex that is not yet in T sub I that is closest to those already in T sub I. So in this part of the algorithm, this is the greedy step because we are trying to get the local optimal solution by choosing the vertex closest to the previous version of the tree. And then, you stop when all vertices are included. So, mag-stop tayo at T sub n if all vertices are already included in the tree. So, if the graph is a disconnected graph, so, of course, hindi ka makakakuha ng one tree lang. You can have minimum spanning forest. But for a connected graph, you can only have one minimum spanning tree for that. Okay, so let's have an example. Let's use the previous example that I showed a while ago. Here's an input graph with 4 vertices, and we have edges, not necessarily complete, and we have edge weights for each edge. So we can arbitrarily choose any vertex. So suppose we choose A. So the next step here is to identify yung next vertex that we will include. So in this example, our T sub 1 is a tree consisting of only one vertex, and that is A. So pagka dumating sa T sub 2, we need to identify yung vertex na closest sa A. In this case, we only have 2 options. We can either include C or we can either include B, but since B has a weight na edge weight na equal to 2, then we choose to include B. So in this case, we are greedily choosing B to be part of T2. And then next, since this is our T2, we will include another vertex from the remaining vertices, and we have C and D. So as you can see, we have 4. C is connected closest to the tree by checking this vertex. So 4. And then this one is connected closest to this vertex using 3. Since D is closest to the tree by this edge, we can add D in our T sub 3. Okay? And then lastly, in our T sub n or T sub 4, we can add 4 and then we highlight the edge kung saan siya closest, and that is via this edge which has an edge weight of 1. Okay, so the algorithm stops if lahat ay colored na, and that is T sub n. So we have 4 time steps if we have 4 vertices, or we have n time steps if we have n vertices in general. Although the Prim's algorithm is an intuitive algorithm for this problem, usually ang challenge for greedy algorithms for a problem is by showing that it is actually correct and it is optimal. So most of the proof for showing that the output of a greedy algorithm is correct is by induction. So so yun. If you wanted to know more about the proof by induction, you can just check this reference. Okay, so there are 2 possible implementation of this algorithm. The first is by using a an adjacency matrix as the representation. So the running time, of course, is different. If we use, let's say, priority queue as an as a data structure for the implementation. So if we use the adjacency matrix as our representation of the graph, then the running time of the Prim's algorithm is n squared. Bakit kaya? It's because we have n iterations. Okay, so we have n iterations, and then for each iteration, we need to identify kung sino sa mga remaining edges yung i-connect natin. So, the parang get the nearest vertex is also n. So, we have a total of n squared. And then, if we have an adjacency adjacency list representation, and by utilizing a priority queue, we can store all the remaining vertices in a priority queue. And then the total running time would be m times log n, where m is the total number of edges and n is the total number of. So the crucial property behind the correctness of Prim's algorithm is because of this claim. So suppose we have a graph that has vertices that is partitioned into two parts. So we have a set x, or a set of vertices na x, and we have a set of vertices na y. And suppose if you partition the graph into two, you can highlight some of the edges that passes through one part to the other. So ito yung mga white edges natin dyan. Okay, so suppose you have a light edge, and that light edge is the minimum weight among all this parang passing through edges. So, and that edge connects x to y. Ang sabi dito sa claim is that the edge xy should be part of the minimum spanning tree. So, this claim or this property is actually true at every iteration of the Prim's algorithm, because you can imagine that this is the set of not yet selected vertices, and this is the part of selected vertices. So from time to time, we are adding one vertex from x to the vertex in y by identifying yung closest vertex from this part to this part. So, again, using the mathematical induction, we can actually prove that Prim's algorithm is correct by showing that the claim is true for all iterations from 1 to n. Another greedy algorithm for the minimum spanning tree is the Kruskal's algorithm. So, the main difference for the Kruskal's algorithm is that we are trying to construct one edge at a time. So, kung yung kanina, one vertex at a time, ito, one edge at a time. So, medyo mas straightforward yung Kruskal's algorithm compared with the Prim's algorithm. So, the first step is to sort the list of edges in a non-decreasing order of length. And then, we try to grow the tree one edge at a time to produce the minimum spanning tree. So, instead of having t sub 1 to t sub n dun sa Prim's algorithm, in this case, we have expanding forests. And initially, we have forest na may mga n trees consisting of individual vertices hanggang sa umabot tayo sa point na lahat sila ay connected na using the added edges. So, on each iteration, we add an edge on the sorted list from item number 1 unless this would create a cycle. So, we skip if that particular edge will create a cycle. So, here's an example. This is the same example that we had a while ago for the Prim's algorithm. What we can do is to sort the edges in non-decreasing order, or sabihin natin increasing. So, we have 1, 2, 3, 4, 6. That's the sorting. So, initially, ang meron tayo is a forest with individual vertices. That's our F1. Ito pala, we have F1. And then on the second iteration, we added this edge connecting C and D because this edge lists edge weight. Okay? And then next is to consider this edge 2. So, since hindi pa rin naman siya nakikreate ng cycle and this is a legit parang forest, we can add 2. For the next iteration, we can add 3. Okay, so okay pa rin siya. This is a connected graph already, but hindi pa nag-e-end dyan yung computation natin. We still go to the next iteration where we will judge if 4 will be included in the minimum spanning tree. And since adding 4 will create a cycle in the graph, we need to skip 4. And then last is we will check if we can include 6. So if we will include 6, this will also create a cycle. Okay, so finally, after traversing all of the edges of this graph in a non-decreasing order and checking if we add this particular edge, will it create a cycle? We were able to create a minimum spanning tree out of that process. So, some notes about the Kruskal's algorithm. Algorithm looks easier than Prim's, but it is harder to implement because we always need to check if a cycle will occur if we will add particular edge. So, yung cycle is created if and only if added edge connects vertices in the same connected component. And this algorithm runs in m log m time with m as the total number of edges. So the time is mostly spent on sorting. We have two algorithms. The other algorithm is m times log n, and the other algorithm is m times log m. Okay, so we can now compare which one is better depending if it's a sparse graph or a denser graph. Suppose we have same n. So if we have a dense graph, it's better to use the Prim's algorithm. If we have a sparse graph with less edges, then it's okay to use the Kruskal's algorithm. Usually, the running time of the Kruskal's algorithm is dependent on the total number of edges. So imagine if this is a complete graph, you will have n squared log n squared running time compared to n squared log n.